Alright, chemists, let's have a look at the Haber process, and in particular, how Le Chatelier's principle applies. And this here is the little summary of the chemical reaction of the Haber process, and it's N nitrogen plus 3 hydrogen gases gives you 2 ammonias. So we're talking about how to build ammonia. Um, so here is our reaction, and here is how it would look if we were to draw it out graphically. So you see you've got 1 nitrogen, 3 hydrogen molecules, and this gives you 2 molecules of ammonia, and they are all gases. So you have 1 mole of this, 3 moles of hydrogen gives you 2 moles all up. And it's really important when we talk about the gases that you have 1 volume of, so a litre being a volume, 1 volume of nitrogen, 3 volumes of hydrogen goes to 2 volumes of ammonia. So it's an exothermic reaction. What this means is there is more energy stored in the bonds of the reactants than there are the products. The implication for us is that means the forward reaction gives you releases energy. It's a reversible reaction, and at standard temperature and pressure, so that's 0 degrees in 1 atmosphere, the equilibrium is established far on the left-hand side, so it favors the reactants. And even in standard lab conditions, which is 25 degrees in 1 atmosphere, it's still far on the left-hand side of that reaction. So the reactants are mostly what you end up with. And we notice we get a large difference in our boiling points. So we've got ammonia up here, which is our product, which boils or turns back into a liquid from a gas at minus 33 degrees. However, hydrogen and nitrogen are both boiling points are sub 190. So they're both, the boiling points are both minus 190 or lower. So one thing we need to talk about when we talk about any chemistry like this is where are we getting our reactants from? Now, just to make sure we're sure of where we are, the Haber process is the industrial synthesis of ammonia. Nitrogen gas, which we use in it, comes from one of 2 ways. It can come from a reaction between natural gas and air. And this removes the oxygen and leaves nitrogen. So that's one thing we can do. But the easier way to do it is the fractional distillation of liquid air. And this is where we go from nitrogen gas to nitrogen liquid. And it's important to realize that because of the covalent nature, you still have the N2. The covalent bond is not broken when it cools down. The hydrogen, on the other hand, can also be obtained through a couple of ways. One is the catalytic reaction, which is the most common way between natural gas and steam. So you react natural gas and steam, and you will get hydrogen. We'll talk about that in a second. And the other one is through electrolysis of water, but that's a very expensive way to do it. So here we see our natural gas, which is mostly methane, plus water, and that's steam because it's a gas, at 750 degrees over a nickel catalyst gives you 4 hydrogen molecules and a carbon dioxide molecule. Now, this is actually a summary. There are a couple more steps to it, which we'll show in a second. The other way is the electrolysis of water. But generally, the catalytic reactions are used to obtain both nitrogen and hydrogen gas. And they just, you just get a purer sample that way. But this one here, as we said, is a summary of a reaction. So we see we go from methane here plus steam gas over a nickel catalyst at 750 degrees Celsius gives us carbon monoxide and hydrogen. Okay, gives us 3 volumes of hydrogen. We then take this carbon monoxide and we react it with steam again over the same nickel catalyst, blah, 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 to give you carbon dioxide and another hydrogen gas. So there's 2 things that's happening. We're making most efficient use of our steam and our products here, our reactants products, to get as much hydrogen as possible. But carbon dioxide is also less of an environmental pollutant than carbon monoxide. And we can see a nice little flowchart here where you've got the methane and steam, and then gives you hydrogen, which we come down here to be put in there. But you can also use that hydrogen to react it with air, which gives you water, and this removes the oxygen out of air. Because remember, air is 78% nitrogen, and there's a lot of air, a lot of oxygen there as well, and this is how we take it out. So let's have a look at the Haber process and how Le Chatelier's principle affects each step of the Haber process. There are reasons behind each decision, so each step in the Haber process, which will maximize production. Now is a good time to have a break. As I said, it's going to be a slightly longer video, so have a break if you want. Pause now, come back. Right here, we have our reaction. We have nitrogen, 1 mole of nitrogen plus 3 moles of hydrogen over an iron oxide catalyst at 500 degrees Celsius gives you 2 moles of ammonia. Now, it is also an exothermic reaction. What this means is that there is roughly 46 kilojoules released for every 1 mole of ammonia. So when you get 2 moles of ammonia, you get 92 kilojoules of energy released per mole. It is a reversible reaction that favors the reactants under standard conditions. So the first step is the gases come in, don't worry about these numbers so much, and enter the compressor. This is a compressor here. It compresses a fan, pushes it all into a smaller volume. This increases the pressure and pushes the reaction to the right-hand side, so further over this way, to relieve the pressure. And the reason it does this is because 4 moles of gas over here, 2 moles of gas there. So it'll push it that way to relieve the pressure. The mixture is then heated to a moderate heat of 500 degrees. It's 400 to 500. 400 to 500 degrees, which pushes the reaction that way. And it does this because it's an exothermic reaction. So the forward reaction is exothermic, so it will try and reduce the heat of the system, and it'll push it that direction. But we do it to increase the rate of reaction. It's a balancing act. So you need to choose between increasing the rate of reaction and increasing the yield. There is some give and take there, because otherwise this reaction would be extremely slow. So it's heated just here, over here, before it enters the catalysts. The reaction then comes into contact with the iron oxide catalyst, and 10% of this will react to make about 10% of the system of the mixture will be ammonia at the end, and it comes through here. We've got ammonia, nitrogen, hydrogen coming out. 10% of it's ammonia. It enters the cooling tank. So this gas mixture enters this cooling tank or a big condenser, and cools to the boiling point of ammonia of about minus 33 degrees. This allows the ammonia to become a liquid, and it condenses out. On top of this, you've also taken ammonia out, so you've taken this out, and that will push, so you reduce the concentration here, which will push the reaction further to the right, because so you've taken some of that concentration away, so it will use this, will make up more ammonia to push that reaction to the right. And then we get it there. Then the final step is that the remaining hydrogen and nitrogen is recycled back through, and it just keeps going around and around and around. So what are the conditions for maximum production? This is the plant, by the way. It's a very, very large plant. These are the cooling towers, so where the condensation happens. Nitrogen and hydrogen are fed in a ratio of 3 to 1. This means we've got the right ratio for the reaction to happen. So these are conditions for maximum production. The pressure of 250 to 350 atmospheres. That's huge. That is a massive, massive, massive pressure. The temperature is between 400 to 500 degrees. It could be much hotter, and the rate of reaction will be much, much faster. But as the rate of reaction goes up because of a temperature, what's actually going to happen is the yield will decrease. The iron oxide catalyst lowers the activation energy, and this allows us to put the reaction at a lower temperature yet again. We reuse the unused gases. They just keep cycling through, and this allows us to have as much as possible in there. Finally, ammonia is constantly removed as a liquid, and again, this drives the reaction in the other direction. Alright, that was a long one. I hope that made sense. If you have any questions, put them in the comments below, and we'll get back to you as quick as we can. Thanks for watching. See you next time. Bye now.